Good morning, people. Welcome to the first lesson on vectors, forces, resultants, etc. Yeah, that's going to be quite a big section. I'll work through a few examples, and as I work through examples, I'll explain various concepts and terminologies, etc. as I go along. Okay. Right, here's the first little example here. It says calculate the magnitude and direction of the resultant in each of the following cases. There's the first one. Okay. Now, this is taken from one of the documents that I put on Blackboard there. Looks like that. It's the first one. I'm going to do the first one there. Alright, calculate the magnitude. Magnitude, another word for magnitude is just size. Okay. So that means that the size of, okay, and direction of the resultant. Now, resultant, new word, I'm sure. Now, the resultant, you must go back and look up and write down the definition for yourselves and learn it, because I'm going to ask it in the first test. The question says calculate the size and the direction of the resultant in each of the following cases. The resultant here is the single force that can replace the effect of these two forces. A lot of students seem to think, oh, it's the single force that's equal to the two. No, it's not. Okay. And if there was three acting, we can find the resultant of those three as well. A lot of students seem to think the resultant is only of two forces. No, it can be of two forces, three forces, five, or however many there are. Okay, in this case, two, we're starting off easy. So the resultant is the single force which can replace the effect of these two forces. Now let's imagine we had a pin sitting over there. There's a pin there, okay, and we've got a force acting 30 degrees that way there. Oh, by the way, before I continue, let me give you a note on convention. Okay, so let me make a note here somewhere. Sign convention. Sign convention. Very, very important. A sign convention is something we're going to use from now until the end of your structural engineering life. Okay, convention is not, for us, a convention isn't something that we go sit and talk and have lots of coffee and get fat. No, we don't do that. It's a set of rules. Okay, right, sorry about that. Right, I suggest you make a note of this somewhere. Right, so that's our north line, that's our south line, that's our east line, and that's our west line. You should all know that. Okay. Now, whenever we measure angles in engineering, we always measure from the east line in an anti-clockwise fashion. Okay. So that will be 0 degrees. That will be, yes, 90 degrees. That will be 180 degrees. And that will be 270 degrees. And of course, when we go back, that will be 360. And once we get back to east, north starts again. Okay. So you can, if I look at, excuse me, sorry. So if I look at that force here, that 30 Newton force is acting at 30 degrees. Okay. So that means from the east line, we measure 30 up there, and it's acting that way like so. Okay. Right, people. So whenever we give a direction, it's going to be given as that over there. Okay. But if you look at the answer here, okay, this answer says 11.7 degrees north of east. There's another format. Okay. Now it goes like this. Are you tuning in? Right, now, this force here acting at 30 degrees can also be written as the following. Okay. We can also say that this force is acting at 30 degrees north of east. Okay. Did you get that? We can also say that this force is acting 30 degrees north of east, or from east. That angle inside there, how much is it? Yes, you know, you're very clever. It's 60 degrees, because that there is 90 degrees. Okay. So we can either say that this force is acting at 30 degrees, okay, with this first convention I mentioned here, or we can say it is acting at 30 degrees north of east, Or what else can we say? We can say it's acting at 60 degrees east of north. That means it's acting 60 degrees that way. Okay? So many degrees from north, and this is so many degrees from east. Okay? Did you get that? Now this convention here, okay, this is written by an author in one of the textbooks. He says this resultant, that's the size of the resultant there, that's the answer, and he says the resultant is acting 11.7 degrees north of east. So that means that angle there is 70 degrees north of east. Okay, so whenever we give a direction of a vector, now remember, you know what vector is. You must need to look up what a vector is. A vector has it's a physical quantity which has sorry, let me just stop this for a second. Right, a vector is something that has two quantities attached to it. It has size and direction. Okay, it has size and direction. For example, a force. This force here is a vector. Why? Because it has size and direction. So this vector is 30 degrees, it's 30 newtons, that is magnitude, and its direction is 30 degrees. We can either say 30 degrees, or we can say it's 30 degrees north of east, or we can say it's 60 degrees east of north. Okay, so whenever we give a direction for a vector, we can write its direction in three possible ways. I'm generally going to use this one over here. Okay, but if I set you a test and you give me an answer, you can either give it like that, or you can give it like that, or you can give it like that. Okay, just as you wish, but get it correct. And as I said in the previous lessons, we're not making cake, we're not throwing a bit of raisins in, we're not throwing a bit of flour in, and a little bit of this, and we're not guessing, it's exact. Okay, so if it's 31 degrees, it's going to be wrong. If you say it's 30 degrees east of north, it's going to be wrong. If you say 60 degrees north of east, it's going to be wrong. Okay, you need to learn it, you need to get it right. So all these answers here is the same answer, and it's the same correct answer for the same thing. Okay, this vector here, this force is a vector. Why? Because it has size, it's 50 degrees, and what's its direction? Yes, we can either say it's acting eastwards, or we can say it's acting at 0 degrees. Okay, so if a force is acting either horizontally that way, it's eastwards. If it's vertically that way, it's northwards. If it's horizontally this way, it's westwards. Or it's vertical down that way, we say it is acting southwards. Okay, so this vector has a size of 30 newtons acting at 30 degrees, and this vector has a size of 50 newtons acting at 0 degrees or eastwards. Okay, right, people, there are other things of vectors. Okay, for example, think about something like, let me just clean my board quickly. Right, people, I'll just clean the board and just tidy things up a bit and just edit things a bit here. I've just redrawn our sign convention there. And people, to add to what I was saying there, forces. Okay, so all forces, all directions are measured from the east line anti-clockwise. Okay, so that's 0 degrees, 90, 180, 270, 271 to the 359, 359, back to 0. Okay, right. Next, very, very, very important thing. Okay, all forces acting vertically upwards. Let me change the color here. Let me make it all forces acting vertically upward is considered positive. All forces acting vertically downwards is considered negative. And all forces acting horizontally to the right, okay, is considered, hang on, let me just change that. I didn't want to do it like, just give me a second. I didn't want to say that. And here we go. All forces acting vertically upward, okay, is considered positive. I'm going to write it like so. Capital F subscript Y. All forces acting vertically downward is considered negative, okay, minus Fy. So it's capital F subscript Y. And by the way, this is like your number line in mathematics. There's the origin, that's north over there. All forces acting horizontally to the right is considered positive, and all forces acting horizontally to the left is considered negative. Okay, I'm going to say that again. Okay, all forces acting vertically upward and horizontally to the right is considered positive. This is forces in the y plane, and this is forces in the x plane. All forces acting vertically downward is considered negative along the y plane, and all forces acting horizontally to the left in the x plane is considered negative. Okay, people, you need to remember that. So sign here, okay, a sign here, minus plus minus, doesn't mean to say that the force going this way is smaller than that one. No, sign here indicates direction. Okay, I mean, if we look at maths and we say minus 6 is a number that's smaller than plus 3. Okay, it's smaller than. Okay, in maths we say that, yes. Okay, but in engineering and applied mechanics, the minus sign indicates direction. If that's a force there, it means there that this force is going to the left and that force is going to the right, or that force is going downwards and that force is going upwards. Okay, so you need to get it worked out in your head. Okay, and then another thing to add there is we have a turning force, turning forces. Okay, if we have a force that's turning like so, okay, we call it a moment, spelled like this, moment, moment. And a moment is very simple, but a massive concept in applied mechanics, theory of structures, and structural analysis. Okay, right. Any turning force that goes clockwise is considered positive, and any turning force that goes anti-clockwise is considered negative. Is that sinking in? Any turning force or any moment that's turning clockwise this way is considered positive, and any turning moment that's going anti-clockwise is considered negative. Okay, the sign again, once it doesn't say that that one is smaller than that one. No, it tells us this one is going that way and this one is going that way. Okay, right. Forces going up to the right is plus, forces going left and down is minus, moments going clockwise is plus, and moments going anti-clockwise is negative. Right, people, that's all for sign convention. I'm not going to mention it again. From now you must know it there. I'm going to clean the board and we're going to proceed. Right, people, the next big thing. The question is find the magnitude and the direction of the resultant. Okay, what's the resultant? The resultant is the one force which will have the same effect of those two forces acting there. So if that's a pin there, okay, and it's being held stationary there, we've got a force acting that way and a force acting that way. If I could replace the single force, what do you think, what's the effect these two forces will have on that there? Okay, do you think a force will be acting vertically upward, leftwards, or downwards? No, I think a force is going to be acting somewhere sitting over like that. Okay, let's call it R for resultant. Okay, so I'm asking the question again. What effect do you think that that force and that force will have on that pin there or that point there? It will act somewhere that way. Okay, sort of in the middle there. Okay, and once we found the value of that, we've answered the first part of the question. Right, now people, the way we're going to do that, we are going to do that by resolving forces, resolving forces into components. That's what we're going to do. Okay, resolve just means to break down into. Okay, what does it mean is it means that any force that is not horizontal or vertical, that means like that one there, we resolve it into components. Now I'm going to take that force and I'm going to draw it here, and we're going to talk quite a bit about it for a start. Right, let me do this. Right, so there's my north-south line, there's my east-west line, and there's my force acting. Okay, 30 newtons. Oh, sorry. 30 newtons. Right. And there's my angle, 30 degrees. Right, now I'm going to complete the rectangle. I'm going to do this. And I'm going to do this. Okay, right. Now, you will agree, okay, that side and that side is equal to that, that side, and that side is equal to that side, okay? And that 30 degree, the 30 Newton force there is my diagonal on the rectangle, okay? We must resolve this force into its horizontal and vertical components. So that's going to be a vertical component, and that's going to be the horizontal component acting the other way. So that's the vertical component, and that's the horizontal component. Now, you need to stay with me here. The vertical component and the horizontal component, these two forces here can replace the effect of that force acting in that direction there. I'll say that again. The vertical component of this force and the horizontal component of this force has the same effect of that one force, the 30 Newton force, acting at 30 degrees. Okay? Now, what we just done, we resolve this force into its vertical and horizontal components. Now, the question is, what is H equal to? And what is V equal to in terms of that angle there and the size of the force there? Can we work it out? Can we write it in terms of that there? Yes, we can. Why? Because we got loads of right angle triangles. And people, this is where you need to know your trigonometry very well. If you don't, you are going to struggle. So that sine theta, cos theta, tan theta, you know it. You need to know it very well. I'm taking my time on this here, as I said on the first one, so we can get it right. And after this, we're just going to state it what they are and continue to all the other problems. Okay, Ryan. I'm looking at this triangle over here, this one over here. Okay, so if I say the cos of 30 degrees is equal to, agree with me that the cos of that angle is equal to the horizontal h over the hypotenuse 30. Can you see that there? The cosine of that angle is equal to the adjacent, which we called h for horizontal, divided by the hypotenuse 30. Okay, so therefore h is equal to 30 times cos 30 degrees. Okay, so we can actually work it out. I'm going to pick up my calculator and I'm going to work it out. You do the same thing and see what you get. It is 30 cos 30 is equal to, it is 25.98. 25, what is this thing? Sorry about that. 25.98. Right. What is it, Newton? Chickens, Ferraris, pairs? No, it is Newtons. If you leave the N out, I take up a mark. Right. Right, we need to solve for V. Okay. Now, do you agree that V here is the same as that over there? Right. So I can use the same triangle. I can say V is sitting over there. So I'm going to say the sine of 30 degrees is equal to the opposite, V, over the hypotenuse 30. So therefore, V is equal to 30 times sine of 30 degrees. Okay, and you should know by now, sine 30 is half of 30 there, so it's 15.00 newtons. Okay, right people, so I've resolved this 30 Newton force acting at that angle into its vertical and horizontal components. Its vertical component is 15 newtons its horizontal component is 25.8 newtons. So if I took this force away, let's say I took this force away. Okay, let's say I took that force away, and I only had that force acting of 15 vertically upwards, and I only had this force acting, that going eastwards. It will have exactly the same effect as the 30 Newton forces acting on its own at that angle there. Did you get that? Okay. What have I done? I've resolved this force into its horizontal and vertical components. Okay, that's what we've done there. Right, people, so now let me consider the other angle. Okay, let me stop this, clean my board up, and let me consider that angle inside over there and see what happens. Right, people, I've cleaned up the board and I've erased this angle here, and of course that's going to be 60. Right, I'm going to resolve components. I'm taking my time with this because I find students, they forever stay confused by this. I've erased angle 30 degrees and I've written in 60 degrees, and I'm going to use this angle to resolve components. Right, so the cos of 60 degrees is equal to the adjacent V over the resultant of 30. So therefore V is equal to 30 times cos 60, and it is equal to, I'm going to work it out like you should do the same. Don't believe me, work it out. 30 cos 60 is equal to, is 15. And notice there, 0.0, by the way, I didn't mention it. We work to 2 places after the decimal in this class, okay? Not 3. You can work to 3 if you want to sometimes for it to improve accuracy. 1 is too little, but we generally work to 2 places after the decimal. A lot of students will write 15 Newton here. It's not exactly technically correct because it could be 15.01, it could be 15.02, it could be 15.13, and so on. So it's 15.00 Newton. Right. Now you will agree with me if that's V there, and this side here is equal to that side, so I can call that side H. Okay, so in that triangle there, I'm going to say the sine of 60 degrees is equal to H over 30. It's the opposite over the hypotenuse. Sorry, 30 Newton there. Right, therefore H is equal to 30 sine 60. And I'm going to work it out. Pick up your calculator and do the same. It's 30 sine 60 is equal to, it is 25.98 Newton. 25, let me make the 5 nicer. 0.98 Newton. Right. What am I saying? When I worked at V previously, what did we get for V over here? We got 50 Newton. But we use that angle there. Okay. We got H as being 25.98, but we use that angle there. Now, are you tuning in? Listen to me very carefully. I think some of you came from schools where the teacher said, if it's horizontal, it's the cosine component. If it's vertical, it's the sine component. That is not the correct way to view that. Okay? This is how I remember it. If I'm using this angle here, okay, this is going to be the cosine component, and that's going to be the sine component using the same angle. Okay. Now watch here. If I'm using 30 degrees, this component here is equal to 30 cos 30, and that one will be 30 sine of the same angle, and that will be 25.9 Newton, and that will be 50 newtons. If I'm using this angle here, then this component adjacent to it is the cosine component. Then this component here is equal to 30 cos 60, which is 15, and the other one there will be 30 sine of 60, which is that one over there. People, you need to get that correct in your brain. Okay, you need to get it correct. A lot of people seem to think that if it's horizontal, it's cosine, if it's vertical sine. It's not correct. It depends on the angle that you are using. Think about it. I'm taking my time here. I'm not going to take my time from this point onwards. I'm taking my time. I'm going very slow at this point because students struggle with this in applied mechanics. They struggle in TOS and they struggle in structural analysis. They get it wrong because they want to guess it. Oh, I think it's sine and cos. No, it's not that. Whether you use cosine or whether you sine depends on the angle that you are using. Okay? Right. That's enough of that. I'm going to clean the board and now we can go ahead and solve this problem over here. Right, people, now we know about sign and sign convention. We know which way the forces go, which way the moments are going, but we get to moments later. And we also understand how to call up the directions. And yes, so and we know how to resolve components. Okay. Now, I'm going to resolve my forces on my sketch over here. Right, let me do this. There's my vertical component of that force, and that's my horizontal component of that force over there, like so. Okay, and I'm going to name it. If that's 30 degrees there, that's 30 degrees, agree with me there. Okay, and because I'm using the angle between the force that's known and the adjacent component, this is going to be 30 newtons times cos 30. I explained all of that. I'm not explaining it again. This will be 30 times sine of that same angle. I'm not explaining this again. I'm going to use it now. Right. People, the next step in the process of answering the question, we sum vertical forces and we sum horizontal forces. So I'm going to say the sum of the forces in the vertical plane, and that is how we say that there. The sum of the forces in the vertical plane is equal to, okay, that's your summation sign that I spoke about the other day. Sum, and that is small y, written like this. Okay, capital F small y, we call that a subscript or a footscript. It's at the toe of the capital letter. Okay, that is how we do that. Right, I'm summing vertical forces. That's going to be plus. Okay, why is it plus? Because from our sign convention, all forces going vertically upward is considered positive. So it's going to be, you can put the plus sign in or leave it at. Doesn't matter. It's 30 sine 30 degrees. Are there any more in the vertical? No. So I can just work it out. So what's 30 sine 30? Sine 30 is off. So that's 15 degrees. Sorry, 15 newtons exactly. Right. And because my answer here is positive, because it's positive, it means the final vertical forces are going upwards. Why is it going upwards? Because of our sign convention. Now people, this sign here indicates direction, and this positive sign here means that this is going upwards over there. Okay, I'm summing horizontals. So the sum of the forces in the horizontal is equal to, how many horizontal forces do we have acting at the joint there? We've got two. We've got this one and we've got that one. And because they're both going horizontally to the right, it will be both plus. So it will be 30 cos 30 plus 50 is equal to, I'm going to pick up my calculator and I'm going to work it out. It's 30 cos 30 plus 50. It is 75.98. Okay. Stop the video, do the calculation, and check if you get the same answer. Okay. Don't just assume I'm getting the correct answer. You work at the answer for yourself. You check mine, and then you continue. Okay. That is how you learn. Right, people? And because my answer is positive here, it means that the resultant horizontal force is in fact going horizontally to the right. Okay. Now people, I'm reading my question again. It says calculate the magnitude and the direction of the resultant. Now people here, this is the sum of all the vertical forces acting. So the net force acting is 50 newtons vertical. This is the sum of the horizontal forces acting, and we see that from this calculation here, that the net force, that means the resultant forces acting, is 75.98 newtons going to the right. But we want the resultant force, right? So from that, we're going to draw this. There's my 50 Newton force acting over there. Let me first finish this off. Newton going upwards. This is 75.98 going horizontal. So if I complete my rectangle like so, notice what we did earlier. I'm not doing the reverse process, okay? And that there is my resultant, okay? So what I'm going to do, there's my rectangle. So I've got 4 right angles, okay? And there's my horizontal component, so that's 15 Newton. And of course, there's 15 that side as well, because of the rectangle. And that side is also 75.98 because of the rectangle. So the question is, what I'm going to do, I'm going to work at that angle there. And I'm going to work at the size of the resultant, which is the hypotenuse of that right angle triangle. And once I find the size of that hypotenuse there, that will be the size of the resultant. And once I find the size of the angle, that's going to be the direction of the resultant. And then it's going to be job done. Then I will have answered the question. Okay, right. And now we're going to do a bit of high school mathematics here. How do I find the resultant there? I'm going to use Pythagoras theorem. Let me just make this a bit small here. Right, so R, the resultant, is equal to 15 squared plus 75.98 squared. 15 squared plus 75.98 squared. And that's equal to that, right? Don't believe, and I got 77.45, 77.45. And people, if you leave out this unit here, I'm going to take a mark off. Okay, that now is the magnitude of the resultant. So we've answered the first part of the question. And yippee, I'm checking the answer. It's nogal the same. So we're doing well. There's the answer, 77.45 newtons. So that is how we arrive at that answer there. Are we done? No, we need to find the direction of the resultant. I'm going to find the angle theta. How do I find the angle theta? I'm going to say the arctangent of the opposite over the adjacent. Let me make this nicer. Let me make this a bit nicer. The arctangent of 15 over 75.98 is equal to, right, work out the answer, stop the video, work out the answer, and check your answer again, my answer, and you only proceed if you got the same answer that I got. And I got 11.17 degrees. I've got 11.17 degrees. Okay, right. And remember I said there's 3 ways to write an answer. Now, if I just extend this over here like so, that's my north line, that's my south line, that's my east line, and that's my west line. Now notice here, the resultant is starting at the origin of those axes over there. So that's going to be, so I can either say my direction is 11.17 degrees. If you stop there, that will be fine. Or I can say it is 11.17 degrees north of east, which is exactly how this author has called it up there. And that's how we got that. So I can say it's 11.17 degrees north of east. Or I can, what will that answer be equal to? I'm going to say minus 90. Or I can say it is 78.85 3 degrees east of north. I'm squeezing it in there, sorry. Okay, so there's the magnitude of the resultant. There's the direction of the resultant. If you stop there, that's fine. Or you can say the direction is 11.17 degrees north of east, which is how the author of this particular question has called it up. Or, I'm saying or, it's either that or that, it's one of the three. Or you can say it's 78.83 degrees east of north. And notice there that those two there must always add up to 90 degrees. North of east, east of north. Okay. Now if you say the direction is, if you tell me the direction of the resultant is 78.83 degrees, it's gonna be wrong. Okay. If you say it's 11.17 degrees east of north, it's going to be wrong. If you say it's 78.83 degrees north of east, it's going to be wrong. It's gonna either have to be one of that, or one of this, or one of that exactly. People seldom get it right. You need to get it right. I will generally write answers like this. Okay, so that means if the resultant was acting somewhere over there, then the direction would be the total angle all the way around to there, and I'll say 180 plus that, but I'll get to that in later. Okay, it's either that or that or that. You need to get that correct in your brain. Okay, right people, so I know I said a lot because I explained all the directions, the sign conventions, and how to resolve forces. I've explained all of that, but just all of this here is how we solve that one over there. So that is how we calculated the magnitude and the direction of the resultant force. So if I put it in plain terms, this force here, 77.45 newtons, acting at 11.17 degrees, is the one force which can replace the effect of the two forces there acting together. Now remember I said there, if we take these two forces there, we predict that the one force is going to act somewhere over there, and yes, we predicted correctly. There's his size, and that angle over there, it's somewhere in between there. If that's 30, it's acting about 11.17 degrees. So we predicted it should act that way, and there we is. So we got the answers all correct. Okay people, that is how we answer that question over there. Okay, so understand the convention, understand the resolving forces. We sum them vertically, we sum them horizontally. If we get a positive answer here, that means the net forces are going vertically. If it was minus, it would have been going down. We sum the horizontal forces here, we got a positive answer. It means the net forces were going horizontally. If we got a negative answer, it meant it should be going horizontally to the left. And to find that, we draw a rectangle out there, and then we use Pythagoras theorem to determine the size of the resultant, and then we use arctan of the one side of the other side there to find the direction, and you state the direction either starting from north or using that convention or that convention there. Okay people, that's me done with the first example. It was far longer because I explained lots of things inside there. So that's it for the first example, and I'll do a few more. I think, yes, I'll do a few more. Let me clean the board and do another example or two. Right people, there's number 2. The question is the same. Determine or calculate the magnitude and direction of the resultant of those two forces. Now let's look at it. We've got a force acting on the north line. We've got a force acting somewhere the other way there. Okay? And the angle between the two of them is 130 degrees. 48 Newton, 61 Newton. Right. So where do we expect the resultant to act? What's the definition of the resultant? The resultant is the single force which can replace the effect of the other forces acting. So we expect it to act somewhere that way. Somewhere that way. Okay? So if we get a force acting this way or that way or that way, we know it's going to be wrong. Right. First thing I'm going to do, I'm going to draw in my north, south, east axis. Okay? I'm going to draw it in like so. Like so. And I'll draw this one like so. Okay. And I'm going to write it in just this once. Sorry. So I'm going to say there's my north line. there's my south line, there's my east line, there's my west line. You will see why I'm writing it in. Okay, and of course that angle inside there is 90 degrees. Right. What's the next thing we do is we resolve all forces acting at an angle into their components. Do we resolve this into components? No, because it's acting vertically. We only need to resolve this one over here. Okay, so let's do that. So I'm going to resolve this one into its components like so and like so. Right, I'm going to use this angle over here. I'm going to use that angle over there. Now, are you tuning in? You never use an angle that's bigger than 90 degrees. So this angle here is not equal to that angle. What's it? What is this angle equal to here? That angle is equal to 130 minus 90. There we go. 130 minus 90 is equal to 40 degrees. Okay. So that angle inside is 40 degrees. So that angle inside there is 40 degrees. You never use an angle that's between components. You never use an angle that's bigger than 90 degrees. It's always an acute angle. It's always an angle that's between 0 and 90. If you use 130, it's going to be wrong straight away. Right. So this component here is equal to 61 cos 40. 61 cos 40 degrees. And that one there is 61 times sine of that same angle. I'm pausing there so you can think about what we said earlier. I'm pausing there. Okay. That component that's adjacent to that angle is equal to 61 cos 40. And that's 61 times sine of the same angle. If I use this angle here, which will be 50, that component will be 61 cos 50. And that will be 61 sine 50, which is the same as that. Right. Now I'm going to sum angles. I'm now going to sum forces. Let's see. I'm going to say this. The sum of the vertical forces is equal to plus 48. Okay. Minus 61 sine 40. Why is it minus? Because it's acting vertically downwards. Minus 61 sine 40. Is equal to, pick up your calculator and you work it out and you check that you get the same answer that I do. Right, what did you get? I got 8.79 newtons. 8.79 newtons. And the answer is positive. That means the net force, vertical force, is going upwards. Okay. Right, I'm summing horizontals. Sum horizontals is equal to, how many horizontal force do we have acting? We've got only that one there. So it's minus. Why is it minus? Because it's going horizontally to the left. So it's minus 1. 61 cos 40. And it is 61 cos 40 is equal to, it is minus 46.73 Newton. And what does the minus sign means? It means the net or the resultant horizontal force is going that way. Okay? And from that now we construct a little rectangle. So I've got the force going like so. Sorry, man. Apologies. And that is 8.79. It is 46.73 Newton. And of course, if I complete my rectangle, it's going to look something like so. Is my resultant, and I am choosing to work at that angle inside there. Right, let's do the calculation. And of course I've got a rectangle, and of course to be able to determine the resultant, the size of the resultant, the famous Pythagoras theorem. Okay, so therefore right, so therefore so R is equal to 8.79 squared plus 46.73 squared. Do the calculation, stop the video, do the calculation, check mine, and continue only if you get the same as my answer. And I got 47.55, 47.55 newtons. If you leave that out, I take a mark over there. And of course, and the angle theta. Now people, listen to me very carefully. Some people just never get this. The angle theta there is just the angle between that component there, which is going westwards, and the resultant. It is not the direction. That's the angle. We come to the direction. Okay. And the angle theta there is arctan of 8.79. I'm trying to squeeze it in here, over 46.73. And what do I get? It is 10.65. 10.65 degrees. Right, now remember the direction. If I draw in my east line and I draw in my south line, and there's my north line. Okay, the direction is always measured from there the other way. So can you see there that that is not the direction of the resultant? It's just the angle between the west line and the resultant there. The full direction in terms of the format that, sorry, oh man, what am I doing? The full direction in the way I write it is that direction over there. Okay, so if that's 10.65, what will it be equal to? The direction will be equal to 180. Why? Because that's 180 minus that there. Okay, so therefore the direction, I'm writing caps, is equal to 180 minus that 132.45 degrees. 132.45 degrees. Okay, or if you prefer to write it the other way, or notice I'm saying or you can say it's 10.65 degrees north of west, or you can say it is 90 minus 10.65, or you can say it is 79.35 degrees west of north. I scribbled there, but okay. Right, people, I'm just going to check my answers again so that I didn't talk nonsense to you. Let me just pause for a moment. Right, people, yes, I have made an error there. I thought I'll just check it quickly. Because sometimes I make an error and then I leave it, and that confuses students. Okay, people, the direction, the angle inside there between the resultant and the west line is 10.65. Therefore, the direction from there all the way around is 180 minus that, which is 169.35 degrees. That's the correct one. Or if you really want to, you can say it's 10.65 degrees north of west, or north from west. Or if you want to use this angle inside here, an angle inside there, okay, of course it will be 90 minus that one there. Or you can say it's 79.35 degrees west of north. So when I mark this, I'm either going to check this one or that one or that one. I'm saying it again. If you say the angle, or if you tell me the resultant is 47.55 Newton, that will be correct. And you say the direction is 10.65 degrees, that's going to be wrong. If you say the direction is 10.65 degrees west of north, that is going to be wrong too. If you say the direction is 79.35 degrees north of west, that is going to be wrong too. It must either be that, or that whole one exactly, or that whole one exactly. Okay, people, that's another example. I might do one more. I'm not explaining directions again. I'm just going to state it, and that's it, and you know why that's there. And remember when we spoke about this example in the beginning there, we did expect, because these forces were acting that way, we said we expect the resultant to be acting somewhere that way. Yes, so we were correct. Okay, this is the one force which can replace the effect of those two forces there, and because they're acting that way, it's going to act in that particular way. And people, notice by the way, this vector here, that's the heads of the vector, and these are the tails of the vectors. The tails of the vectors all radiate from the same point. Can you see that? Okay, this resultant here can't act like so. Okay, that will be wrong. They all start from the same point. From the tails all start from the same point like that there. So if we have a force, acting like so, and we have a force acting like so, we can guess the resultant must be acting somewhere over there. If we have a force acting like so, and we have a force acting like so, and we must guess it's going to be acting somewhere over there. Are you getting the picture? All the forces, their tails emanate from the same origin over there. Okay, so yes. So that's all I want to say about that. Now, people, just while I'm on it, let me just clean the board just a little bit quickly here. Right, people, I've just cleaned the board and made some adjustments there. So the resultant there is 47.5 up Newton. Theta is 10.65 degrees. That's just an angle. And the direction is 180. All of that minus that, because the full direction, the direction I've written in that formula there. So 180 minus 10.65 is 169.35. So that answers the question there. Right. If the question asks you what is the equilibrant, there's its spelling, equilibrant. Another example, another definition you need to look up, equilibrant. I'm just going to say it. You need to go and check it out and look it up yourself. Equilibrant. Okay. Now that there is the resultant. Okay. Now the equilibrant is equal to the resultant. I'm going to call this E. But opposite in direction to the resultant. So if I take this line of, we call this a line of action of the force here. If I take this line of action of the resultant and I just extend it all the way down there, and it's going the opposite way, that there is the equilibrant. Okay, so the equilibrant is equal to the resultant, but opposite in direction. Now, think about this. We know that the resultant has the same effect as those two forces acting there. So do you agree with me? If I take the resultant away, okay, and if I have that force acting there and that force acting there, and I put the equilibrant over there, okay, now remember the equilibrant is equal to the resultant but opposite direction. Can you see there that if I put the equilibrant over there, acting along with that force and that force, that this force here will balance out the 48 Newton force and the 61 Newton force? Can you see that? Okay. The equilibrium there, which is equal to the resultant, remember the resultant has the same effect as those two forces there. If I put the equilibrium there to act along with that force and that force, that this equilibrium will balance out those two forces there. What does it mean? It means that this point here ain't going anywhere. It balances out those two there, and we then say that this whole system here, this whole system is in equilibrium. Very important. Very important for structures. Equilibrium. We say that that system there is in equilibrium. Okay. Now, where you're sitting, I'm assuming you're sitting inside a room. Okay. There's walls, there's a roof. What does the roof want to do? The roof actually wants to fall down on our heads. But thank heavens, structural engineers said no, it's not going to happen. Okay. But because of gravity, that's where loads come from. Because of gravity. If we never had gravity, we would never have loads. Okay. But because the roof wants to fall down because of gravity, but the walls push up in the opposite direction by the same amount. Okay. That whole system, when I call it the system, the roof, the walls, the ground, the soil below you, the chair you're sitting on, that whole system is in equilibrium. Even though the forces are acting, even though the wind is blowing, even though the earth is tremoring, remember we had an earth tremor some months ago, even though snow is laying on your roof, even though water is laying on your roof because of rainwater, even though the wind is blowing against your roof, against the walls, even though all that is happening, the structure is going nowhere, it's because that whole system of forces that are acting all the time, they're going nowhere, it's in equilibrium. Now that concept, people, is very, very important in structures. Okay, so, and another word for equilibrant is reaction. Reaction, very important word. Reaction. Or. Okay, so that's the resultant, but the line on, but acting on the same line but opposite direction is the equilibrium or the reaction. Okay, so this here is actually the reaction of that force and that force acting on that point there. Okay, that means the reaction has the same effect as all the forces acting together, but in the opposite direction there of that resultant. Okay, people, now in this section, that's all I really want to say. I'm going to do another example, and from this point onwards, you will understand the resultant, you will understand equilibrium, you understand the reaction, you understand convention of forces, and plus, minus, you understand direction of turning forces, and you will know how to resolve forces into the components, and some vertical and some horizontal. Okay, people, I'll stop this video here. I'll do 1 or 2 more examples because this video is very long. I'll do 1 or 2 more examples where it will go a lot quicker because I've explained a lot of concepts under those 2 examples. Okay, people, thank you for your attention, and I shall see you in the next video.